In this video, we're going to be evaluating planar mechanisms, and in particular, we're going to be looking at a slider crank mechanism. We're going to do this in a number of ways. First of all, we're going to determine a range of parameters using scale drawings, and then in the next video, we're going to determine the same parameters using trigonometric methods. So at the bottom of the screen, we have a sketch of our slider crank mechanism. Now please note that this diagram is not to scale. And in this first method, we're going to need to produce a scale version of that particular sketch. Now in the bottom corner, listed in red, we have some of the variables that we're going to be aiming to calculate or determine. First of all, we have VBO. Now just to explain some of these terms, VBO means the linear velocity of point B relative to point O. Well, if we refer to our sketch, we can see point B represents the slider, and point O is the origin, or where our movement originates from. So if you can imagine the link OA, so this 80mm link on the right hand side, is rotating with an angular velocity of 85 radians per second. As that rotates, point A is going to circulate around point O. As point A circulates around point O, our slider is going to move backwards and forwards like so. The slider is constrained, so it can only move in the horizontal plane, and what we want to determine is the velocity of the slider relative to the origin at the point where this internal angle equals 55 degrees. The velocity of the slider is going to change as that angle changes, and it's going to oscillate backwards and forwards. So that's the first thing that we're going to determine, the linear velocity of the slider relative to the origin, or the velocity of point B relative to point O, when we have an angular velocity of 85 radians per second and an internal angle of 55 degrees. The next thing we're going to determine is the angular velocity of point B relative to point A. Well, we have a link AB that's 250mm long, and what we need to determine there is the angular velocity of B relative to A. So by angular velocity, we know that point B relative to point A is going to be travelling in one of these two directions here. Point B is always going to remain a fixed distance from point A, but the angular velocity of point B relative to A is going to be dependent again on that internal angle of 55 degrees. We're then going to determine the angular acceleration of point B relative to point A, and again, because its angular velocity is changing, we just mentioned that we have an angular velocity of B relative to A, but because that angular velocity is changing, the angular acceleration is also changing. Then finally, we're going to determine the force required to move our slider relative to our origin. So the force of B relative to O. So there's quite a lot of work involved here, but the key to solving these problems is to produce accurate scale drawings. Now the first scale drawing I'm going to produce is of our geometry that's shown at the bottom there. And I'm going to use that to determine some of the unknown angles within this triangle. So let's begin with our datum line, and I'm going to sketch this at the top of the page. We have our datum line, and from that datum line, I'm going to specify the location of point O. Next, we have an 80mm crank at an angle of 55 degrees. Now I'm going to represent 80mm as a 4cm line. So 80mm is equivalent to 4cm. Therefore, I'm dividing by 20. So I need to draw a 4cm line at an angle of 55 degrees. So the first thing that I need to do is I need to position the centre of my protractor on point O, and then from the datum line I need to measure 55 degrees. So from this point here I need to measure 55 degrees. Now, if you're doing this with a regular protractor, then you would make an index mark in line with the 55 degrees, so around here somewhere. Then I can draw my line 4 centimeters long in that direction. So 4 centimeters long in the appropriate direction, like so. 1, 2, 3, 4. So now I have the location of my point A. Next, I need to determine the position of my point B, and I know it's going to be somewhere on my datum line, and I know that the length needs to relate to 250 millimeters. Well, we already have our scale factor in the top right-hand corner. 250 millimeters dividing by 20 is equivalent to 12.5 centimeters. So I need to draw a line that's 12.5 centimeters long and attaches to my datum line somewhere over here on the left-hand side. So again, I'm going to take my ruler. The line needs to go through point A like so, and it needs to be 12.5 centimeters long. But I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.5 centimeters. Now finally, I can connect the bottom of my triangle, like so. Okay, now from my scale drawing, I can determine some of the unknown angles. We already know that the angle here is 55 degrees, but I want to know the angle on the left-hand side. So again, I can use my protractor. I need to make sure I place the center of my protractor at the point like so. And then I can take my measurement. So my measurement here is 15 degrees. Now I therefore know that my remaining angle is 180 minus 55 minus 15. So this remaining angle here is going to be 110 degrees. You can measure it if you prefer, but now I have my 3 angles. So now we have an accurate scale diagram of the geometry. Next we're going to produce an accurate scale linear velocity diagram. So at the top we have our geometry. Next I'm going to produce a linear velocity diagram. Okay, so the first thing to note from our linear velocity diagram is that we can work out the linear velocity of point A relative to point O. And the important thing here is that the linear velocity of point A relative to point O on our original sketch is perpendicular to the link. We know that from angular motion that the linear velocity at the outside of the circle is perpendicular to the radius. So here we have a right angle. Now if we had a horizontal datum line through point A here, then we know from opposite angles that this angle here is 55 degrees. Now because we have a right angle, we know that this angle here is 90 minus 55, or 35 degrees. So we know the direction of point A relative to point O because the angular velocity of that linkage was clockwise. That was indicated on the original sketch. But we can also determine its magnitude. We have a simple equation for converting between linear and angular velocities. V equals r omega. Well, in this instance, we're trying to find the velocity of point A relative to point O, which is the radius of that movement. Well, the radius between point A and point O is 80 millimeters from the beginning of the question. So that radius is the length of OA, the length of that linkage. And the omega that we're interested in is the omega of point A relative to point O. So now we can input some values because VAO, the velocity we're trying to find, is the length of the linkage, 80 millimeters. Well, 80 divided by 1,000 is 0.08. And we need to multiply that by the original angular velocity of 85. Note that the angular velocity is already in radians per second, otherwise we would have needed to convert that to SI units. The velocity of A relative to O equals 6.8 meters per second because it's a linear velocity. Okay, now we're going to try to plot our linear velocity diagram. We know the direction of the velocity of A relative to O is 35 degrees from the horizontal, and we also know that its magnitude is 6.8 meters per second. So this time I'm going to use 6.8 centimeters to represent that. If you're using a ruler and protractor to construct this, then you need to make sure you start with a horizontal datum, and then you need to draw a line 6.8 long, or an equivalent scale, at an angle of 35 degrees. Now, I'm fortunate that the ruler I'm using indicates the angle, but that can just as easily be done using a protractor and ruler. So I need a line 6.8 long. 1, 2, 3, 4, 5, 6.8, like so. I'm also going to remove my datum line to avoid any confusion. The line I've drawn there is VAO, which we know is 6.8 meters per second. Its direction is up and to the right, like so. Now, if we think back to our slider at point B, we also know that that can only travel in one direction. It can only travel forwards or backwards or horizontally. Therefore, we know that the velocity vector is going to be horizontal. We don't know its magnitude or its size at this point, but we do know its direction. So what we can do is we can add a construction line. Recall that this is point O, this is point A, and now we're trying to find the velocity of B relative to O. Well, our velocity of B relative to O needs to go through point O like so, but we also know that it needs to be horizontal. Now finally we need to think about the velocity of point B relative to point A. So if we refer to point B on our diagram, point B is moving relative to point A, and it's going to have a direction. Now, for the same reasons discussed earlier, the velocity of point B relative to point A is going to be perpendicular to the linkage. So we have an angle of 15 degrees plus an angle of 90 degrees, meaning this angle here is 105 degrees. Now we can either use that angle or we can use this angle, which is going to be 75 degrees. It's 75 degrees because it's 180 minus the 105, or 180 minus 90 minus 15. So there's a number of different ways of arriving at the same value. Now we already know the position of point A, and what we're trying to find is the position of point B, which is going to be down here somewhere. So we need a construction line at 75 degrees going through point A. Now once again you can do this just as easily using a ruler and protractor, but fortunately the ruler on here indicates that I already have an angle of 75 degrees there. So for the purposes of my construction line, going through point A, I know its direction is going to be like so. Now I can finish constructing my velocity diagram because I have the velocity of B relative to A here. Its magnitude is 1, 2, 3, 4, or let's say 4.1 for that length. So that's velocity of B relative to A equals 4.1. Now, because I'm using a 1-to-1 scale, 4.1 centimetres is 4.1 metres per second. And next, I can add on the velocity of B relative to O. The velocity of B relative to O is 1, 2, 3, 4, 5, 6, 6.7 centimetres. And 6.7 centimetres for the velocity of B relative to O is the same as 6.7 metres per second. So what I've managed to determine there is one of my original requirements, the velocity of B relative to O, or the velocity of the slider as it moves towards the origin. Let's add that to our right hand side. So we have 6.7 metres per second. The next thing I'm asked to calculate is the angular velocity of B relative to A. Well, once again, we have the formula V equals R omega. Therefore, omega is just V over R. Well, in this instance, I'm trying to find the angular velocity of B relative to A. Therefore, I can use the linear velocity of B relative to A divided by the radius. Well, the radius of motion here between points A and B is the length of that linkage. So the length of the linkage, AB. And we know the original length of that is 250 millimetres. Okay, so we have the velocity of B relative to A from our scale drawing is 4.1 metres per second. That's already in SI units. Divided by the length of AB. Well, the length of AB is 250 mil. Divided by 1,000 is 0.25 metres, giving me an angular velocity of B relative to A equal to 16.4 rads per second. Now, once again, I'm going to add that to my list of variables on the right hand side. So I have omega BA equals 16.4 radians per second. Okay, so we have a diagram for our geometry, and we have a diagram for our linear velocities. Next, we're going to produce a diagram for our linear accelerations. So I've created some space and I've transferred some of our calculated data to the right-hand side. So we had the linear velocity of A relative to O was 6.8 metres per second, and the linear velocity of B relative to A was 4.1 metres per second. What we're looking to calculate now is the angular acceleration of B relative to A and the force required to move the slider. And both of those things are going to come from our linear acceleration diagram. But first of all, we need to construct an accurate scale diagram. Now, when a component rotates, there's the opportunity to have two different types of acceleration. So if this crank here is rotating, then we can have two different linear accelerations. The first linear acceleration would occur if the angular velocity of the crank was changing, in which case we would have what's called a tangential linear acceleration. Now, we know from our initial conditions that the angular velocity of our crank is remaining constant at 85 radians per second. Therefore, we aren't going to have any angular acceleration because the velocity is constant. But what we will have is a centripetal acceleration, and centripetal acceleration acts back towards the origin of rotation. That's our linear acceleration centripetal. Now, the simplest way to think of this is an acceleration towards the centre of the crank, and if that didn't occur, point A would just continue off in the direction of motion. So there must be an acceleration towards the centre and a force towards the centre in order to prevent that from happening. If you were to imagine spinning round on a roundabout, then you need to apply a force in order to keep yourself towards the centre of the roundabout. Otherwise you'd be thrown away to the outside. So we can have tangential accelerations if the angular velocity is changing, but any rotating component is going to have centripetal accelerations. Fortunately, in our mechanism, our centripetal accelerations act in the direction of the linkages, or share the same direction as the linkages. But we still need to calculate some of their magnitudes. So we've already established that the tangential acceleration of A relative to O equals 0, because there's no change in the angular velocity of the linkage OA. But what we need to calculate is the centripetal acceleration of A relative to O. And we have a couple of different choices here. We can either use the formula v squared over r, or we can use the formula r omega squared. Now the radius that we're referring to here is the length of the linkage OA, because that's the radius of the motion of the linkage OA. So our radius is the length of OA, which is 0.08 or 80 millimeters. And our angular velocity of linkage OA was specified at the start of the question here, so times 85 squared, and that will give us the centripetal acceleration of A relative to O. Running that through the calculator gives a value of 578. It's a linear acceleration, so our units are meters per second squared. Now, if we consider the point B relative to O, we know that its motion is constrained in the horizontal direction. So it can only have a motion in this direction. As it can only have motion in that direction, it can only have an acceleration in that direction. So the acceleration of B relative to O must be horizontal. There isn't a centripetal and tangential component to that acceleration. Next we come on to the linkage AB, and we need to determine the acceleration of B relative to A. Now in this instance there's two different accelerations. There's a centripetal acceleration acting back towards the origin. The centripetal acceleration is going to point back towards A. It points back towards the centre of motion. But there's also going to be a tangential acceleration, and the tangential acceleration of B relative to A is going to be perpendicular. So we have a centripetal acceleration of B relative to A, but we also have a tangential acceleration of B relative to A. Now once again, we can calculate the centripetal acceleration, because the centripetal acceleration of B relative to A is the same formula as we used previously, r omega squared, except this time the radius of the motion is the length of the linkage AB, and the angular velocity is the angular velocity of B relative to A, which we have down here from our earlier calculation. Therefore, in place of radius, we use the length AB, which was 250 millimeters, or 0.25 meters. And for the angular velocity, we have a value of 16.4, which needs to be squared, which gives us a centripetal acceleration for B relative to A of 67.24 meters per second squared. Now, as mentioned earlier, we could have also used the formula AC equals V squared over R, and we would arrive at exactly the same answer. So we can either use R omega squared, or we can use V squared over R. It makes no difference. So let's make a note of our two centripetal accelerations, and then we'll decide on a scale factor in order to produce our linear acceleration vector diagram. Okay, so we have a centripetal acceleration for A relative to O of 578, and we have a centripetal acceleration of B relative to A of 67.24. Now I'm going to divide each of those values by 50 in order to get a length in centimetres. So we have AC of A relative to O is 578 over 50, which equals 11.6 centimetres. And we have a centripetal acceleration of B relative to A equal to 67.24 over 50, which equals 1.3. And I've just done each of those to the nearest 0.1 centimetres or nearest millimetre, as that's something that I should be able to draw with a relatively high degree of accuracy. So I need a vector AO of length 11.6 centimetres at 55 degrees from the horizontal. Recall that the centripetal acceleration acts in the same direction as the linkage towards the centre of the motion. So from A towards O. So first of all, I need a datum line. And on that datum line, I'm going to add my point O. So somewhere here on the datum line, I want my point O. So I'm going to take my protractor. I'm going to place the centre on my point O, like so. And I'm going to measure down 55 degrees, like so. If you was using a standard protractor, you would just make an index mark here at 55 degrees. Next, I'm going to draw the length of the line as 11.6 centimetres in the direction of O towards my index mark. So from my index mark, I need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.6, which just about fits on my page. And that line there represents the centripetal acceleration of the link AO. Next, I can add the centripetal acceleration of the link BA. The point in the bottom here represents the point A, and I need to draw a second line at an angle of 15 degrees, represented here by our acceleration of B relative to A, so at 15 degrees from the horizontal. I'm going to start with a second datum line, a horizontal datum. I then need to measure up 15 degrees, so I place the centre of my protractor on my point, like so, and measure 15 degrees. Again, you may need to make an index mark to ensure that you're in the right position. And then I need to draw a line of length 1.3 centimetres in that direction. And I'm going 1.3 centimetres. So I have 1.1, 0.2, 0.3. So next we can make a couple of important observations, because we've said that the tangential acceleration of B relative to A is perpendicular to the centripetal acceleration of B relative to A. So I've just measured an angle of 15 degrees here, but our tangential component is perpendicular to that. If it's perpendicular, we need to add 90 degrees. 90 plus 15 is 105. I'm just going to mark the end of that new line on the vector diagram, because that's going to be the starting point for our tangential acceleration. So from that point, I need my protractor. And from that point, I need to measure an angle of 105 degrees. You could add a new datum line if you found it easier to do so. But I know that my zero line is here. And I'm going round 105 degrees this time. Like so. Now, I don't yet know the length of this line, but I know it originates at the new point, and I know it goes at an angle of 105 degrees because it's perpendicular to the orange line that we've just drawn. So I'm going to add a line on there. I'm just going to remove some of these construction lines, and then we'll clarify what we've done there. So I'm going to remove each of my angular construction lines, and I'm going to remove this datum line along the bottom here. And I can also remove this angular construction line here. Now, the same as we did with the velocity diagram, we can now complete this diagram. We have a length here that's 1, 2, 3, 4, 5, 6, 7, 8, 9.4 centimetres. Let's make a note of that. And we have a line along the top that's 1, 2, 3, 4, 5.3 centimetres. Now, just as a reminder, the line that we drew here was the centripetal acceleration of B relative to A. The line that we drew here was the tangential acceleration of B relative to A, noting that the centripetal and the tangential accelerations are at right angles. So we have a right angle here in the bottom corner. The remaining acceleration then is the acceleration of B relative to O. And the line that we drew at the start was the centripetal acceleration of A relative to O. We have some additional lengths on here. This length here was 11.6 centimetres, and the centripetal acceleration of B relative to A was 1.3 centimetres. So let's clear a little bit of space and then we can carry out our final calculations. So we have two things left to calculate. We need to calculate the angular acceleration of B relative to A. And the way that we do that is by using the tangential acceleration. The reason it's the tangential acceleration and not the centripetal acceleration is because the centripetal acceleration just acts back towards the origin. So to determine the angular acceleration of B relative to A, we can use the formula A equals R alpha. It's another one of our conversions between linear and angular motion. But we want alpha, therefore alpha is A over R. As mentioned, the A value that we're using is the tangential acceleration of B relative to A. And the radius that we're using is just the length of the linkage again, the length of the linkage AB. Therefore, the angular acceleration of B relative to A equals 9.4 centimetres times our conversion factor of 50. That would get us back from a distance to an acceleration value, and the length of AB is 0.25. That gives us an angular acceleration of B relative to A equal to 470 over 0.25, which equals 1880 rads per second squared, because it's an angular acceleration in SI units. Incidentally, the 470 on the top of that fraction there represents the tangential acceleration of B relative to A. So 470 metres per second squared. Let's add that to our list of variables and then carry out our very last calculation. So we have 1880 rads per second squared. Once again, we just need a small amount of space for this. So in the bottom left-hand corner, to calculate force, we use mass times acceleration. Well, we know the mass of our slider is 3.5 kilograms, and the acceleration that we need to use is the acceleration of B relative to O. So we have a mass of 3.5. The acceleration of B relative to O is 5.3 centimetres times our scale factor of 50. So we can simplify that. That's the same as 3.5 times 265. and 265 is our acceleration of b relative to O. So we can add this to our diagram. 265 meters per second squared, just for completeness. Therefore, the inertial force comes out as 928 newtons to the nearest whole number. And that completes our data in the bottom right-hand corner, 928 newtons. So just a quick summary of what we've done there. We've used scale drawings, first of all, to produce an accurate geometry to represent our slider crank mechanism. And the reason we needed that was to determine the internal angles within the geometry. Once we had our accurate geometry, we produced a linear velocity diagram. And the important thing to remember there is that the velocity of a linkage acts perpendicular to the linkage. So the velocity of A relative to O was perpendicular to the linkage AO. The velocity of B relative to A was perpendicular to the linkage BA. And finally, we knew that the slider could only move horizontally because it was constrained. Once we determined all of our unknown velocities, we were then able to calculate the centripetal acceleration of A relative to O. In the top right-hand corner, we had a value of 578. And we was also able to calculate the centripetal acceleration of B relative to A. Using that information, we produced our linear acceleration diagram, noting that the linkage BA had a centripetal component as well as a tangential component. Once again, the acceleration of the slider was constrained to horizontal direction, and we were able to determine the direction of the centripetal acceleration of AO because we knew it acted in the same direction as the linkage OA and towards the origin O. So there's a number of different steps there, but the important thing to being successful with these scale drawings is drawing the diagrams as accurately as possible. You need to use a sharp pencil, you need to set up datum lines to make sure your angles are accurate, and you need to measure lengths and angles very accurately throughout the tasks.